Mathematical analysis of recursive algorithms. So what we saw last time was how to go from non-recursive algorithms, those which only had loops, to the complexity analysis of these algorithms. So what we're going to do this time is we're going to eliminate this simplifying assumption, and we're going to look at recursive algorithms, look at their complexity. So the first algorithm that we are going to look at is very simple. It's just the factorial function. Right? So we know that n factorial is n into n minus 1 into n minus 2 down to 1, and in particular 0 factorial is defined to be 1. So we can actually write this recursively. We can say that for n bigger than 0, n factorial, so this is for all, by the way, this inverted a stands for all. So for every n bigger than 0, n factorial is given by the following formula. It's n times, and now notice that this whole thing is just n minus 1 factorial, right? So it's n times n minus 1 factorial. So this is a recursive formulation, and this gives us immediately a recursive function for factorial of n. If n is 0, return 1, otherwise return n times factorial of n minus 1. So to begin with, as usual, we will see what the formal algorithm looks like. It's very simple. Right? So this is all there is to it. We have an algorithm factorial which takes as input n, and now if n is 0, you return 1, otherwise you return the same function applied to n minus 1 multiplied by n. So that's just n into n minus 1 factorial. Okay. So again, remember that this is a number theoretic function, so the input is actually not n but log n. But what we want to do is estimate its complexity, just for simplicity, as a function of n. Right? So let us write m of n as the number of basic operations for input n. So the basic operations in factorial, as we saw, one is to check whether n is 0, and the other one is to multiply it by the recursive result of computing factorial of n minus 1. So it turns out that because of this, we can transfer all the work to computing factorial n minus 1 in this calculation itself. We can say that m of n requires one more step than what you need to compute factorial n minus 1. So assuming that this is correctly computing the number of basic operations for factorial with that input, then factorial of the n minus 1, so this is what happens when you say factorial n minus 1. Okay, it's supposed to take this many steps, and then you have one more step. Okay, we are saying 1, it's actually 2, but we are saying 1 because we're ignoring constants. So one more step. So we have basically converted our recursive definition of the function into a kind of recursive definition of the complexity function. And of course we need one more fact without which this definition will not be complete, which is that if n is 0 in that special case, so this is actually when n is bigger than 0. Okay, and if m is 0, n is 0, then m of 0 is 1. That is, if n is 0, we just do one check if n equal to 0, and then we directly return 1. Okay, so together, okay, this is called a recurrence or a recurrence relation. Okay? And this second part is very important. So this is what is called the initial condition or the base case. Sometimes it is called the base case. And as we will see, without specifying the base case, you may not have a unique solution, and changing the base case will change your final answer. It may not change it by a dramatic amount, but you will get a different answer depending on what you assume is the base case. And together, this recurrence relation we have to solve in order to compute m of n for a given n. Right? So it's important to recognize that there are two different things going on. So at one side you have a recursive algorithm, and this is a function that calls itself and computes a value. On the other side we have a recurrence for its complexity. Right? And if we solve this recurrence, then we get an estimate of the complexity for every input n. Right? So the recursive algorithm computes the answer of that you are looking for in the algorithm, and the recurrence, if you solve, it computes the complexity of that algorithm. So let's write out this recurrence again. So we have m of n is equal to m of n minus 1 plus 1, and m of 0 is equal to 1. So how do we solve this? So the simplest way to solve this is what is called backward substitution. So what we do is we keep expanding and we look for a pattern. right? So we look at in general, so this, remember this M of n, the first case is for n greater than 0. So we start with M of n, and we say, okay, M of n is M of n minus 1 plus 1. Now, if n minus 1 is not 0, then we can, of course, expand this using exactly the same thing. So we can say that this is now for n minus 1 going to be M of n minus 2 plus 1, right? So that is the expansion of this using the same formula, plus 1, okay, which is M of n minus 2 plus 2. Now by the same logic you can expand M of n minus 2, and you can say this is M of n minus 3 plus 1 plus the 2 outside, of course. And so now I'm going to get M of n minus 3 plus 3. And now once you've expanded it a few times, you begin to see a pattern. You get, so as this is going up, this is n minus what you're subtracting from n is going up, what you're adding outside is also going up. So you can show, and you can show it formally, but we won't. So you can show that this will now expand out so that after some n steps, you'll have M of n minus I plus I, right? And if you keep going, what happens is eventually as I is growing, I will become n. So eventually you will come to M of n minus n plus n. But now of course this is 0. So you get M of 0 plus n. But M of 0, and this is where the base case comes in, M of 0 is the initial condition, it's 1. So this is equal to 1 plus n. So this tells us that this factorial function will actually make n plus 1 or order n multiplications. So we use the initial condition M of 0 is equal to 1 because when we reach the final step, we have if n equal to 0, return 1. And since both conditional checks and multiplications are treated as basic operations, we have one basic operation even when n equal to 0. Now in the textbook, okay, only multiplications are counted. So if only multiplications are counted, then the n equal to 0 case has no multiplication, and so we end up with M of 0 is equal to 0, and therefore if we go back to the original calculation, if M of n by backward substitution is M0 plus n, then this is actually 0 plus n, which is n. And this is different from our answer, which is M of n is equal to 1 plus n. So this is just to illustrate that the choice of the initial condition can actually determine the choice, the value that you get in the end, right? So the fact that we ended up with n and the book ends up with n plus 1 is because it's a different choice. And in fact, you can easily verify that if you take any constant m0 is equal to c, then you will end up with M of n is equal to c plus n, because in the final step you will substitute c for M of 0. So when we looked at non-recursive algorithms, we had come up with a general strategy of how we were going to estimate it. And here the strategy is pretty much the same for estimating the complexity in recursive functions, except that instead of summations you use a recurrence. So the first thing you do is you identify the input, what constitutes the input size. Okay. The second thing you have to do is you have to identify the basic operations. And then you have to characterize the dependence of these basic operations on the input size. For every input, do you do the same number of basic operations for every input of a given size, or does it depend on the values themselves? So then depending on that, you have to worry about worst case, best case, etc. Okay. So so far, everything is exactly the same as it would be for a non-recursive algorithm. Now what changes at the next step is that instead of writing a summation, you write a recurrence relation with initial conditions. Right? So this is the basic step now. You have to write a recurrence relation with initial conditions to compute the total number of basic operations. And then of course the hard step, which is to solve the recurrence, okay, for which we use this backward substitution method. So you basically expand the recurrence and you look for a pattern. So let us look at another example. Okay, and this is another example which is very classical. Okay, and this is the towers of Hanoi. So as we know, the Towers of Hanoi puzzle is one where you have three pegs on which you can put disks which have holes in them. So let us call these pegs 1, 2 and 3. So initially you have some collection of disks on one of these pegs, and each of these disks is of a different diameter and they are stacked up in descending order of diameter. The biggest one is at the bottom, the smaller one is above it, and so on. And now the rule is that you cannot put a bigger disk on a smaller disk, and the goal is to take all these disks and move them from 1 to 3. Right? So you want to move disks from 1 to 3 without ever putting a larger disk on a smaller one. And of course you can't do that if you had only one other peg, because if you move the top disk from 1 to 3, then you can't put the second one on top of it because it's bigger. So that's why you have 2. So 2 is, so you are using 2 as the auxiliary, what is called the auxiliary peg. Okay? So there's a temporary space in which you can maneuver around. So this has a very standard solution, a standard recursive solution. So we will not write out code for it, we'll just describe it in words. Okay. So what you do is that you're trying to transfer n pegs, so presumably you know how to transfer n minus 1 pegs. So you move n minus 1 disks, not to 2, not to 3, but to 2. So from 1 to 2 via 3, that is using 3 as the basic thing. So now at this configuration, now you have, right, so you have the biggest disk is still sitting here, and on 2 you have all the other ones, right? So now you can take this disk and move it there, right? So at this point you can move the largest disk from 1 to 3. And now you have another version of this n minus 1 problem. So you move n minus 1 disks from 2 to 3 using this, which is now empty, as your auxiliary, right? So the standard recursive solution says first move n minus 1 disks to the middle guy, then move the biggest guy to the last peg, and then move these n minus 1 to the last one, again using the recursive solution. So now again we write m of n for the number of moves required to transfer n disks. So what is the basic move in this? Basic move is to take one disk from one peg and move it to another peg. So how many times do we need to move disks from one peg to another to transfer n disks from 1 to 3? Okay. So as we saw, we have to first move n minus 1 disks from 1 to 2. Then we have to move one disk from 1 to 3. And then we have to again move n minus 1 disks. Okay. So this is provided n is greater than 1. If you have at least 2 disks, then you have to do this. So this is 2 into m of n minus 1 plus 1. And the base case or the initial condition in this is m1. So m1 is just 1. Right? So when you have only one disk, then in one move you can move it directly from 1 to 3 and you're done. So again we can use this backward substitution idea and look for a pattern. Right? So we start off with m of n is equal to 2 times m of n minus 1 plus 1. Okay, so this is the basic thing for n greater than 1. And for n equal to 1, which is the initial condition, right, we have m of 1 is equal to 1. So we expand m of n, we get 2 times m of n minus 1 plus 1. Now assuming that we have not hit 1 yet, because n minus 1 is still bigger than 1, we can expand this. So we get 2 times, and then this, when we expand, we get 2 times m minus 2, m of n minus 2 plus 1, okay, and we still have the outer plus 1. So we have just taken this part and written the same thing out, except for n, we have used n minus 1 here, so this becomes n minus 2. So now if I write this out, I get 2 times 1, so I get 2 into m of n minus 2 plus 2 plus 1. At this point it's not easy to see the pattern, so let's do it one more time. So again I expand this, okay, so I get 2 times, and now what's inside this red bracket is 2 times m of n minus 3 plus 1, okay, and outside I'll just keep it as 2 plus 1 just to illustrate. I won't simplify it yet. Plus 2 plus 1. Okay. So this plus 2 plus 1 just goes from here to there. I have not made it 3 for a good reason. So now if I expand this out, okay, then what happens is that I think I made a mistake. So this is 2 squared, right? So I had 2 times 2, right? So 2 squared m of n minus 2 plus 2 plus 1. So 2 squared into 2 m minus 3. So now I'm going to get 2 cubed, because 2 squared times 2 into m of n minus 3. And then the remaining term is going to be 2 squared times 1. So it's 2 squared plus 2 plus 1. Okay. So now a pattern is beginning to emerge. This is going to be 1 plus 2 plus 2 squared. Next time it's going to be 2 cubed and so on. And it's useful to remember that this is can be simplified as 2 cubed minus 1. Right? So this, if you think of it in binary, right? So if you think of it in binary, so 2 to the n will be 1, okay, and then a bunch of zeros. Okay, so this is 2 to the 0, 2 to the 1, 2 to the n minus 1, and 2 to the n. So this is 2 to the n in binary. So if I now have 1s here everywhere before that, this is the number 1 less, which is 2 to the n minus 1. So this is 2 to the n minus 1 is 2 to the n minus 1 plus 2 to the n minus 2 plus blah 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 plus 2 to the 1 plus 2 to the 0. So this is what exactly we have here. 2 cubed is equal to 2 cubed minus 1 is equal to 2 squared plus 2 to the 1 plus 2 to the 0 is equal to 2 squared plus 2 plus 1. So this is the simplification that we have used, right? So going back, we have reached a situation where we have m of n is 2 cubed times m of n minus 3 plus 2 to the 3 minus 1. So this is the pattern, and if you're not sure, you can always expand it some more, and eventually you will realize that this is 2 to the I m of n minus I plus 2 to the I minus 1. Now we stop when this thing becomes 1, right? So we stop with I equal to n minus 1. So eventually we get 2 to the n minus 1 m of 1 plus 2 to the n minus 1 minus 1. Remember that m of 1 is just equal to 1. So this becomes 2 to the n minus 1 plus 2 to the n minus 1 minus 1 is equal to 2 times 2 to the n minus 1 minus 1 is 2 to the n minus 1. Right? So this tells us that our recursive algorithm for the towers of Hanoi requires 2 to the n minus 1 moves for n disks. Okay, so this is clearly an exponential algorithm, and this is exponential because the problem is hard. It's not because the algorithm is poor. It's because the problem is hard that we have an exponential algorithm, and perhaps it is instructive to remember some of the mythical. So we have these monks. So in one version of this Tower of Hanoi puzzle, we have monks transferring 64 disks. Okay, and when they finish, the world will end. So the question is, do we have to be worried about this or not? Okay. But so we know that transferring 64 disks is going to take 2 to the 64 minus 1 steps. Okay, and assuming a reasonable amount of time taken for each step, even if you take a very minimal amount of time for each step, this is longer than our sun will, the sun around which the earth moves will survive. You know that all stars eventually kind of live out their lifetime and they expand to giants and then they collapse into something like a black hole. So the sun is going to move into that state much before this ends. So the monks can keep doing whatever they want and we need not worry. The world is not going to end in our lifetime. Now in this particular problem, another way to see how this works is to draw the tree of recursive calls. Right? So we have this, if we actually wrote it out as a piece of code, we'll have, say, Hanoi, let's call our function Hanoi of n, is going to call twice Hanoi of n minus 1 because it has to do this twice. And each of these in turn is going to call Hanoi of n minus 2 twice. Right? And this is going to go all the way down until we reach call Hanoi of 1 at the leaf. Right? So we have now a complete binary tree, okay, whose height is n. Okay? So this will have 2 to the n minus 1 nodes. And every node corresponds to one function call and therefore one basic move. So every time you call this function, you have to move one peg. So you are looking at the number of times you move pegs and therefore you have 2 to the n minus 1 total moves. Now as a last example, okay, let us revisit the problem of counting the bits in the binary. So I believe this is example 3 and not example 4, sorry. Counting the number of bits in the binary expansion of a decimal number. Right? We saw a non-recursive version which kept dividing by 2. Okay? Now you can replace that division by 2 on that loop by a recursive call. So there is a very simple recursive way of doing the same thing. So here is the algorithm. It's not the old binary of n, but bin rec for binary recursive. So this says if n is 1, then you just return saying you need 1 digit. Otherwise, you compute the number of digits you need for n by 2, the floor of n by 2, and then you add 1 to it. Okay, so this is a very direct representation of the process of dividing by 2 in a recursive way. So here the interesting thing is that if you want to write a recurrence for this, okay, so if you want to count how many steps this takes, so let's call it say a of n, okay, then it's clear that a of n first requires you to solve the problem of size an by 2 and then one more. Okay, so you have to basically take the number of digits there and do so. You have to do one addition at this point. So this plus 1 is the addition and it corresponds to the addition step that you do after you make the recursive call. So now the problem with this is that in order to use backward substitution, you have to somehow work through this floor function. And if you take random values of n, you'll end up with big problems when you're doing this backward substitution. Right? So we will assume that n is a power of 2. Okay, so this means that n is of the form 2 to the power k for some k. So then 1 will be 2 to the power 0. Right? So of course we have to go back and mention in this recurrence that a of 1 is 1 because that's where we stop. So now if we write out the same recurrence again in terms of k, then we say that a, if n is 2 to the k, then it requires us to compute a of 2 to the k minus 1, that is what happens when you divide by 2, k to the k minus 1 plus 1, and a of 2 to the 0 is equal to 1. So this is an equivalent recurrence restricted to the case where n is a power of 2. So now you can use backward substitution, right? So this recurrence. So use that famous backward substitution method. So you just expand. So you say a 2 to the k is equal to a 2 to the k minus 1 plus 1, and now you use the same expansion here, and so you will get equal to a 2 to the k minus 2 plus 1. Okay, so this is the expanded thing plus the old one. So this is a 2 to the k minus 2 plus 2. And now the pattern is much easier to spot. If you do it one more time, you're going to get a 2 to the k minus 3 plus 3. And then if you keep going, you get a 2 to the k minus I plus I. And so when after k steps, you'll get a 2 to the k minus k plus k. Okay, and this is now 2 to the 0. So this is going to be 1 plus k. But what is k? Well, remember that k is taken from there. So we had that n is equal to 2 to the k. So k is nothing but log to the base 2 of n. Right? So this is going to be equal to 1 plus log to the base 2 of n. So in this case, by looking at the special case for n, where n is the power form 2 to the k, we can use backward substitution effectively to get a nice answer. So now the question is this valid or not? And it turns out that this can be justified. So using only n equal to 2 to the k to backward substitute. Right? So what about all the other n? Okay. So there is something which we will not explain formally, but there is some kind of a smoothness theorem for recurrence occurrence, which says that the result holds for all n. When we go from non-recursive to recursive algorithms, okay, what we do is we use recurrence relations. For the time complexity. And having set up a recurrence relation, then we typically use this backward substitution to solve it. There are some, there is a rich theory of recurrence relations, and some patterns are complicated even to do with backward substitution. And so you have to actually work carefully to do it.